I'm really excited that you've all joined us. This is going to be a bit of an experiment. This is the first time that we're using the Crowdcast platform, so do bear with us. We're learning as you are. Today, we're actually going to be listening to Ben-Sasson talk about the story of how zero-knowledge proofs and blockchain got together. And so I'm very excited to invite you, Ellie. Just a quick note to everybody. You can see that there's like a chat in the sidebar. Feel free to add stuff there. And there's also this ask a question at the bottom. So in there, you can ask a question and then people can like vote on it. And so this might be something fun for us to play with at the end. Okay, now I'm going to pass it on to you, Ellie.
Hi, so hello everyone. Can you hear me? Can someone say in the chat box if you can hear me? Okay, great. Okay, thanks so much. So what I'm going to do is most of the time I'll just be talking and doodling on this here thingy, which I hope you can also see shared. So like this thing. And I have a very bad handwriting, as you can see. It gets even worse when using this pad. But anyways, I want to try it. And I'll be doodling as I'm talking. So I'd like maybe for, say, hopefully half an hour or so, tell my own personal story, which is a very, it's just one tiny story about how, my very theoretical research led me in a very gnarly way to end up doing things related to zero-knowledge proofs and actually be involved in by now 2 startups. So it's this personal story. I hope you'll enjoy it. And then after these 30 minutes, I'll leave like 15 minutes just to answer general questions and, talks and whatnot. So here we go. I guess for me, the starting point was basically in 2001, and it was through this thing called the PCP theorem. So the PCP theorem actually was discovered. It's a sequence of works, but it basically is attributed to, Aurora in Sudan, Aurora and Safra, and then this other paper, it's called ALMSS, Aurora Lund Mutwani, Sudan Segedi, and all of this was in 1992, so this was way before my time. The PCP theorem was one of these marvelous things that actually came out from this whole marvelous area of interactive proofs and zero-knowledge proofs that started about 7 years earlier with this model of interactive proofs. And it comes from this branch of computer science and mathematics that's called complexity theory. It's this attempt to understand how hard it is to compute certain things and what kind of languages or generic classes of problems you can solve in different models. And the PCP theorem is still this very day hailed as this amazing and very surprising result. And the PCP theorem talks about the ability to check the correctness of a proof extremely efficiently. So often it's explained in this sort of informal way that suppose you get this very long proof of some very important theorem, like the Poincaré conjecture or the Riemann hypothesis or something like that. It's really, really long, and you don't wanna read all of it. So you would like to ask for some way to encode it so that you could check it really, really quickly by, let's say, flipping through the pages and just reading a very small number of symbols from it. And the PCP theorem gives this very generic reduction that allows you to take any statement and ask for a specific encoding of its proof in such a way that you can read a small number of bits from that proof. And this number can be made as small as 3 bits. And in general, the number of bits that you need to read depends only on the error you're willing to tolerate and does not depend at all on the length of the theorem, on the length of the proof. So even if the proof is 1 million pages long, if you want to be sure with certainty of at most 99.999%, you only need to read something like 50 bits from the proof, and you will know with very high likelihood that the proof is correct. So this was, at the time, was an absolutely amazing revelation that you can sort of speed up the the process of checking the correctness of proofs, and you can do it for a very generic class of computations. And so this was before my time, as I said. And in 2001, I started my postdoc at Harvard and MIT, and I went to two amazing professors at the time, Salil Vadhan from Harvard and Madhu Sudan from MIT, who now is at Harvard. And I basically started my postdoc with them. And I came to them and said, look, I'd really like to, do whatever you guys are doing. And one of the questions was, how large is a PCP proof? So what we mean is, suppose the standard proof, the standard witness for your statement, this is the original proof of the Fermat theorem, let's suppose its size is n. And we know we can reduce it to this PCP proof that usually is denoted pi, from which you can read, 3 symbols and already know the answer. But, how large is pi? What is its length in bits? And it was already known that it is at most it is at most the length of the original witness raised to some power. This power was a small constant, something like roughly 2 to the 2 to the 100. I mean, this is actually, the constant was probably a little bit bigger. But for the price of this, you could actually get to read only 3 bits from the proof. So as you can imagine, this sort of constant is a little bit too big for anyone's comfort, even though as theoreticians, everyone's sort of happy with any sort of constant. As long as it's a polynomial, everyone's happy. But the question I was asked was basically, can you bring down this constant to something smaller? And this was a question that we all worked on. So, with Salil Vadhan and with Madhu Sudan, with many others at the time over a number of years. And we did bring it down. So the main sort of result from that very theoretical work was that you can actually get the proof pi to be smaller than what's called quasi-linear in n. And this was a long sequence of work, but this particular result was from my work with Madhu Sudan in roughly 2005, sort of. So this symbol means, now I hope I can go down a little bit, or maybe all I can do is sort of just decrease this thing. Now I'm going to have a hard time. Oops. Okay, so this means O of n times some log to power c of n. And this particular c wasn't too bad. It was like maybe 4 or something like that. So this was, a kind of nifty work in theory of computation. But this was, we were all very happy with this result back in the time. So this was 2001. Then I guess if I could, how do I move this thing down? No, never mind. Let me just, I'll continue without this thing, and maybe we'll later on add another. Oh, okay, here's the next page. So that was 2001. Then around 2005, oops. No, that's not what I want. Look, this is too complicated for me, so I'll just go back and continue speaking, and some other time I'll learn how to use this thing. Okay, so that was 2001. We started with very theoretical work, and then around 3 years later, there was someone by the name an excellent young researcher, Alma Bhattacharya, who's now a faculty member. And he, as a summer project, he took part of this result and wrote code for it as sort of a graduate project at MIT. And he wrote code for this part that is related to Reed-Solomon codes. So he wrote code for part of this project. And at first this looked very strange to me. Like, why would anyone want to encode this thing? What use could one have for this thing called the PCP theorem? But, I guess students have to do summer projects. Anyways, 2 years later, I was teaching a course in theory. And then I just taught this theoretical result of the PCP theorem. And 3 students came up. This was 2007. And they said, we want to do a summer project at Technion, which was where I was teaching at the time. And I said, well, there's this thing called the PCP theorem that by now we have pretty efficient proofs. Someone wrote code for it, for one half of it, for what's called the proximity testing, but no one wrote code for the other half, which is sort of the arithmetization and the reduction from a computational problem to a problem about low-degree polynomials. Would you like to do it? And they said, yeah, why not? So they did a summer project in which they took, rewrote the code for the part that talks about testing low-degree polynomials, and they added to that another part that does the reduction. And they submitted a student project, and there it lay. They got like prizes at both the Faculty of Computer Science and at Technion for like best project of the year, but wasn't published anywhere. We didn't do anything with it. Then another year later, I saw that as a theoretician, as a mathematician, I saw that folks could write code for these things. I had no idea why someone would want to do it, but it actually can be done. A year later, I received this very sizable grant as a researcher from the European Research Council, and this grant was almost 2 million euros, and that's a huge sum in any institution, and in an Israeli institution, it's way over what you can, actually spend as a theoretician, because grad students and postdoc salaries are only so much, and you can't start employing a whole bunch of them. So I thought that maybe it might be a good idea to actually write code for this for this thing. And I received the grant, and right after that I was asked actually to go and meet Eran Tromer, who was a postdoc at MIT. And discuss with him opportunities for him coming to work with us at Technion. And I just received this grant, and I told him, look, we have this nice grant. Why not sort of use it to work together on proof systems? He told me that he had just written a very nice paper with a young graduate student by the name of Alessandro Chiesa from MIT. So Eran was a postdoc there, and Alessandro was a graduate student, and they wrote something about like recursion of proofs and incrementally verifiable computation. And they thought that it might be a good idea to try and actually instantiate that thing with a real proof system that might be useful. And I thought to myself, okay, there was already one project that worked, and why not? So I was in Israel. Eran Tromer was doing his job talks. We met, someplace in Caesarea. I said, look, that's a reason for you to come to Technion. He ended up going to Tel Aviv University, but I said, look, irrespective of that, why don't we start working together? And he said, yeah, there's this really smart graduate student. We'll all enjoy collaborating with him. So I said, sure, let's bring, both of you over. So, I started spending my grant by inviting both Eran and Alessandro. And at the same time, I had another graduate student who wasn't my graduate student, but he was at Technion by the name of Daniel Genkin. He's also a faculty member these days in the US. And he was also interested in this stuff. So we started this collaboration that ended up being Skipper Lab. And we ended up hiring a number of programmers who were actually undergraduates at Technion, and asked them to sort of work with us together on encoding some PCP system for real computation, including a compiler and from general C code. In hindsight, I think that was too big a thing to try and swallow, but we thought that it would be a short project. Took a very long time, but we had a lot of fun. So all this time we're writing this code for converting programs written in C into PCP systems, okay? And we had this nagging feeling that, you know, why would anyone use this? And I remember multiple discussions in different settings, like, why exactly are we doing this? And the best justification I had at the time was something like, okay, I have this huge grant to spend. You know, why not? Worst comes to worst, we'll write a bunch of papers and we'll submit them. And then about the papers, there's also a very interesting anecdote, which is, so as we're building the systems, we're also speccing them out and like writing in more details the reductions that take a general program to a proof. And at this point, so this was already going on for like a year or two, and everyone was deeply involved. And you know, I have to, it's a funny story to recount, but like I was initially very opposed to publishing any papers before the code is ready. And I remember this particular discussion with Alessandro was, you know, pushing for writing the papers. And I said, look, it's not a good idea because this is such a simple reduction that if we publish the paper, someone's just going to beat us to writing the code. And also, like, who in the world would ever, you know, care about such reductions in papers about them? And, you know, Alessandro was very persuasive, and I sort of backed away, and I said, okay, yeah, let's write these papers. So two things happened. I mean, three things happened. It wasn't that easy to take those papers and actually convert them to code. Each one of the papers turned out to be like this very detailed, you know, with a lot of information, a lot of good insights that people are citing and using and building on till this day. And it certainly took even us a large number of years, like 5 or 6 years, from those initial papers to the, you know, to anything that resembles a system. Okay, so this whole time, there was this PCP track going on. Now, starting around 2008, there was this other, so the PCP theorem is very complicated to implement because of this thing that is called low degree testing that I'd be happy to talk about some other occasion. But it's this like big, tough nut that people try to avoid. And in 2008, there was a beautiful paper from several colleagues of mine that initiated this other line of attack that led to the, you know, to the snarks and many other constructions. And it said, well, let's try to use additively homomorphic encryption to bypass and sort of replace this tough nut of low degree testing. And this was an initial paper by Ishai, Kushilevitz, and Ostrovsky, and it led to a large number of improvements by Groth and Sahai and others that said, oh, you can use bilinear pairings to make it you know, a publicly verifiable system. And this progressed very quickly and culminated in an amazing construction, the GGPR quadratic arithmetic program construction that is implemented in the Pinocchio paper, which was the first, you know, implemented snark of, you know, the snarks that are as in Zcash. And then when we learned of this, we said, oh, look, you know, let's go and also implement this thing. And again, I can confess that I was sort of, you know, I was a purist saying, no, let's go and continue with the PCP approach because we're almost there. It's like a month away. It's like, you know, we're just there. It's transparent and it's much better and post-quantum secure. And yeah, it was mostly Alessandro who brought on Madar Zvirza, another, you know, amazing collaborator. And then they said, no, but this is a much faster approach, so let's go and implement it. And I thought, no, it's not much faster. It's, you know, but you know, again, I sort of came along for the journey, and what a fun journey it was. So indeed, that was much faster, as we all know. You know, the snarks came out way before the starks, and okay, and now we started having, so we had like we had understandings in both worlds about arithmetizations and how do you do things efficiently, and we combined them in several ways that, again, we can leave to some technical discussion. And now we had the beginning of an inkling of something that you could actually think of deploying or showing a proof of concept, okay? And this was already around 2013. So both in the snark and in the Stark world, there were things that looked a little, you know, that you can start to talk about them. And at that time, I was in the U.S. for a sabbatical, and I was just going to return home, and I thought the systems weren't quite ready. Okay, but I thought, as long as I'm here, why don't I, and it's all local, I'll do like a tour among several universities and give talks and talk about this thing. So I started preparing a talk, and I thought of some motivating examples, right? We've been for 5 years now, since around 2008, sorry, maybe 2010, sorry. Project started 2010, so for like more than 3 years, multiple people have been spending time writing code. The question why, like what are the applications for which someone will want this, were not something that we dealt with. So I remember, sort of scratching my head and trying to think what would be good examples. So one example was that there was just this big debacle with a launch of a game. I think it was SimCity 5 was launched, and it immediately crashed because the game logic was all run on central servers, and there were too many players who wanted to play the game. It was a centralized system. So the servers are all crashed, and actually the CEO had to resign, and the stock dropped of that company. So I said, oh, the reason is, here's one motivation. The reason is this whole thing happened is because the game company cannot rely on the players to sort of report what they did. There's no computational integrity, so they have to do everything, and this is the reason this crashes. And then I cooked up some weird examples about sort of, Internet of Things style, sensors reporting temperatures in a nuclear facility or things that didn't quite stick. And this was 2013. So before that, a number of times people have asked me, what do you think about Bitcoin? Because they assumed I do computers, so maybe I understand something about Bitcoin. And my reaction to all those cases was, it's nothing, and I actually didn't bother to go and read the paper or look anything up. If I could have a time machine, I would go back and start mining or buy Bitcoin or something. But so as I was trying to think of other examples, at some point I said, let's look at Bitcoin. And then it seemed like Bitcoin, which I didn't fully understand, was another good example for explaining why this thing that we're doing for 3 years now might be useful. Okay, so I added that. And then again, it was, so Alessandro said, there's this Bitcoin guy, Gavin, coming to speak at MIT about Bitcoin, and I thought that I'd meet him, but I was just on my tour. So I tried to reach out, and I noticed that there's actually a Bitcoin conference in San Jose, and I wrote to Gavin and said, could I, I'm on my tour anyways, could I come there and speak? And they said, yeah, sure, come and speak. So I landed at the Bitcoin San Jose conference, and this was by far the most electrifying, positively electrifying event I think I ever attended, certainly in my sort of professional career. There was this sort of Woodstock messianic vibe in the air of we are now changing history for the better. Like it was amazing experience, especially for someone who came always, the only conferences I ever attended were ones of mathematicians with like 100, smart mathematicians and not a lot of vibe and so on. So, and there I gave this talk that I also, that I shared, the video still exists there. And that was, for me, the watershed moment. And in hindsight, the eureka moment, even though at the time I couldn't articulate what it was that led to this. But in hindsight, I think what happened was that all the conventional examples and conventional use cases we came up with, banks. Would you like banks to use proofs, ZKPs, and prove that what they're doing is okay? Sure, you would like, but would they want to do this? No, you need to trust them. They won't do that. And so on and so forth. Would you like the government to prove to you something? Yeah, sure you would like, but the government's not going to prove to you anything. You're going to trust it. I mean, it's going to tell you either trust me or, that's what the law says or something like that. So whenever you came to a conventional business or enterprise and said, oh, we have this thing such as a ZKP, you can prove computational integrity with it, you can speed up verification. Usually the kind of questions, and it's pretty much the same this day. The questions are, okay, what exactly is this? Who exactly is proving what to whom, and why would you do this? And do we really need it? Okay, you know what? Let's settle for a POC and put it as a bullet, on the presentation to the board. And in stark contrast, in the world of blockchains, the reaction has and still is always the same. It's not, what is this good for? It is, where is the code? Here are 5 different use cases that if the code is up to speed, we want to use it for it now. And the reason is that in blockchains, in decentralized blockchains, you really, one of the core principles is that of inclusive accountability. And anyone should be able to check and verify that everything is correct without having any trust assumptions or minimal trust assumptions about the rest. So this was like this watershed moment for me in hindsight. Sort of dragged me slowly into the world, like this sort of merging proofs and blockchains. At the same conference, even though I'm not sure we got to meet there, I don't remember already, but also Ian Myers was at the very same conference presenting the zero coin paper, which is this other beautiful result, right? The first use of some general purpose zero knowledge in the context of blockchains to achieve some form of privacy. And shortly after we, sort of the teams, the John Hopkins team, and our team the main characters that were involved in this particular effort at the time were Alessandro and Eran and Madels and myself. And we wrote this zero cash paper that was an academic paper, but also with code implementation, relied on the SNARK that we built, which was an improvement to the Pinocchio system and had some added benefits. And sort of we published that paper. Okay. And after that time, we received a number of inquiries about, trying to do something commercial with this. Most of these inquiries didn't sound too promising, but one of them stood out, and that was the one by Zuko, who was and still is exactly the right person to lead such an effort, all the right ideological and personality reasons. So sort of the co-authors of that zero cash paper and Zuko's team, I think initially it was Zuko and Nathan and Dara, but very quickly there were Sean Bowe and Taylor at the time and others. We sort of joined forces, and what is now called the Electrocoin Company was started, which led to the Zcash cryptocurrency that is still a thing out there. I think a beautiful thing. The amount of tailwinds for adoption of zero knowledge as a thing in the world, I think to a large extent is a lot of the credit goes to Zuko and his amazing team of engineers that took what was first completely academic and then semi-academic. The zero cash paper is sort of has some code implementation, but then made it into a product. So that was Zcash. Now, all of this sort of came out of this SNARK branch that, even though it goes, it still relies on PCP techniques. So this branch that uses SNARKs comes from this, from this sort of older branch, this realization that you should use additive homomorphic encryption to remove the hard parts of the PCP theorem. And that paper is called, I think, like linear PCPs or without PCPs or something like that. Like, let's remove the hard part and do things differently. But at least for me, my passion was always, even just from puristic, mathematical reasons, it was sort of on the, what was now called START, but back in the day, and then still in some part of my mind, I still think of it as like PCP style proofs. And by PCP-style proofs, one means proofs that have a lot of information, theoretic proofs to them. So there's a lot of math going into them, a lot of algebra and probability, and to prove that certain functions are low-degree polynomials. And there is rather minimal use of cryptography, only to get a commitment scheme, right? So you try to minimize the amount of crypto and the amount of cryptographic assumptions that you use, and you maximize the amount of provable information theoretic math. And I have to admit that the main reason I still like this approach best, first and foremost, is because of the mathematician side in me that likes this sort of pure, it has more math and more proofs and less cryptographic assumptions. So, but it also turns out to be, because of these reasons, turns out to be post-quantum secure, have linear cryptography, be transparent, no trusted setup, and faster arithmetic, a whole bunch of other benefits. But again, at least for me, at least initially, it came from this sort of puristic mathematical inclination. So we continued along this path of what turned out to be Starks. At first, they were called, when they were first published, it was called actually Psi, which I think means succinct computational integrity. So they had no zero knowledge in them, and they were way less efficient than what we have now. By this time, two very important additional team members that I want to point out are Ariel, actually three of them. Ido Bentov, that joined our team, and he's also a big name in cryptocurrencies in general. Ariel Gabizon, who was at the time working with us on these things, and of course Michael Ryabtsev, who started as an undergraduate as a programmer, but sort of matured into a mathematician and scientist who, on top of doing amazing engineering, also is behind many of the brilliant improvements that sort of bridge the gap between something that's very theoretical and not really efficient, and something that's actually extremely efficient. Things like the Frey construction, the star construction, the use of interaction for merging together many constraints into something that's much faster. So we worked together on this Psi thing. There was, again, a publication and some open source code. And then, there was one more thing that needed to be done. And this was sort of making the proofs even shorter and tighter and whatnot. So all of the first implementation relied very much on this 2003 result called the Ben-Sasson Sudan PCP of proximity. And it's pretty efficient theoretically, but not so much in practice. So there was this, now that construction actually uses this analogy between PCPs and this thing called fast Fourier transform. Because at some very deep level, these things, and by now we understand this much better than we have in the past, and probably in 10 years we'll understand it even better. With every year that passes, we understand these things slightly more better. Efficient PCPs and efficient proof systems have very deep connections to efficient Fourier transforms, finite Fourier transforms. And this is a topic that I'd be very happy to dedicate a special talk to, and just go over fast Fourier transform, how to view it, and how to see that it is very similar to proof systems and the connections between them. So in the Ben-Sasson Sudan paper and the constructions that are built on it, there is this sort of fast Fourier transform, but it uses parameters in a very inefficient way. And they are so inefficient that there are certain attacks on them. So back in the day with Ido and Ariel and Michael, we started analyzing the sort of security or the ways to attack PCP systems. And we noticed pretty serious attacks. We even wrote a paper about it. This paper, we tried to submit it like 5 times. It got rejected from every possible venue. It's still out there. We tried to improve the write-up several different times. I should say that along this route of theory to practice, there was a very long period of time in which most of the papers that we wrote took a very long time to get accepted to, even decent or semi-decent academic conferences. And I guess, at the time it was frustrating. Like for instance, the Stark paper got rejected. I think it was accepted on its 5th submission. The Fry paper was accepted on its 3rd or 4th submission. And, it takes time for like this, especially when like the theoreticians, like one thing, the practitioners like this other thing. But as you're going this route, they don't understand it and they don't understand it. And neither one of them likes it. So it's a little bit like walking in the desert to the promised land. But, I think by now this is past. So anyways, there was this, we had this understanding that there are some things in the Ben-Sasson Sudan construction or the use of the FFT that is extremely inefficient. And at the same time, we already had a much better understanding of this new concept that was modeled. It was, floating around in a large number of our papers, this notion of how to use interaction in oracles, what was formulated as the interactive oracle proof model. In this paper with Alessandro and Nick Spooner, who's another extremely influential researcher in this effort, along with Tom Gu and a few other from Alessandro's team. So in this model that you allow yourselves a lot more rounds of interaction, you can sort of choose the way you do your sort of FFTs very differently. And this led to a much faster and more efficient in terms of proof size construction, which is the Fry construction. And with this sort of missing link, so this Fry protocol, which is a cornerstone in Starks and many other efficient implementations along the Stark branch, the sort of PCP-based thing, and is a topic that I continue to be deeply interested in, and along with many of the other folks at StarCore and others in our sort of academic advisors and people in this team. This was sort of the missing piece in order to build something slightly more efficient, which led to Starks. Now, all of this is still sort of research-wise and so on, but I just want to mention sort of how sort of StarCore, which was the second startup, came along. So Zcash would describe it as, we wrote an academic paper. This amazing team came along, right, which was led by Zuko, Nathan, and Dara. And basically, we did some sort of handover, said we were going to help as much as we can, but, our involvement was, or my involvement at least, I'll speak only for myself, was not as large, In this other case of Starks, sort of already got the bug. For a long time, whenever I had any question about business, I had this good old friend from 30 years who was always my business advisor in all things, by the name of Uri. And we spoke many times on business-related aspects around the formation of Zcash and other things. But first and foremost, we were just very good friends. So at some point, we sort of popped the question, should we maybe work together and do this thing? And so when I say we, by this time it was it's clear to everyone that Michael Ryabtsev, my co-founder and chief architect at StarCore, was deeply leading basically the Stark and Fry effort, and Alessandro Chiesa, longtime collaborator on all things ZKPs and proofs, and Uri, we sort of joined hands together. We had a lot of luck, today we're in this coronavirus and markets crashing and everything. We started this effort in the fall of 2018 as the price of Bitcoin was going like this. So, you know, we're very lucky with the timing. And yeah, that's how StarCore was founded. So sort of to summarize, I guess, just this personal story that again, I don't like, what are the takeaways or like what happened? I personally was drawn by pure math and never did I think that I'll be doing anything practical. At some point, for reasons I don't fully understand, I got drawn into participating in academic implementation projects. And then I would say that sort of Bitcoin happened to me. In particular, it was May 2013. And yeah, since then I was bitten with a bug. And, you know, it's this amazingly unexpected story. So that's what I wanted to share. I see that according to the time, like, you know, 40 minutes have passed, but I think that like 5 or 6 we spoke. So I'll be very happy to answer questions. And before that, I want to say that, so I haven't had time. I was focusing on just speaking, so I didn't read any of the comments, but I just want to say that if there is interest in maybe having another more math drill down into, let's say, this informal analogy between fast Fourier transforms and certain kinds of proof systems, transparent proof systems, and relations to polynomial commitment schemes, and, you know, open questions there, and the way the algorithms work. I have nowhere to go right now, and I think a whole lot of you have nowhere to go as well. You know, unless you're in, I guess, China or Singapore or Southeast Asia, right? So we could do, you know, another one maybe next week or something like that. An informal, but math dedicated. So no more, you know, stories by the fireside. Okay, so I'll take questions if folks are interested or comments.
Hey, Ellie, I'm going to rejoin now. So if you click on the bottom bar, it says ask a question.
Yeah, I see that.
Click on that, and there's actually a few that have already been voted to the top.
Yeah.
Maybe I'll say them. I mean, I don't actually know how the video capture works on this, so I'll just say them out loud, and then you can take them. So the top one is, when do you think we'll see ZK proofs used outside of the blockchain market? Where will it be first?
Okay. I mean, it's very hard to make predictions, and especially in these days of the coronavirus, right? So, you know, so I have an excuse if this, I would say that the first place outside of pure blockchains where we'll see ZKPs really used in, I would guess that that would be in the general gaming, you know, not blockchain related. Because, and I'll say why. I think that first of all, we see a lot of gaming coming closer to blockchains, and it makes a lot of sense. But even if blockchains weren't around, games are already of immense economic value. You know, the digital gaming industry is larger than the music and movie industry combined. So, and that's not because of blockchains, right? And in that world, we are all transporting ourselves even and immersing ourselves even more and more in virtual reality and in this digital space. Now, there's a lot of value there, right? You know, there are certain people are making or spending millions, actually billions of dollars on various assets and things and games that are all virtual in the digital world. So the notion of the need to sort of have proofs there and have computational integrity, I think, is a very big need. So I would guess that the first place outside of blockchains would be the digital gaming space, though it might actually start from digital games somehow on blockchains, and then sort of spin out to sort of general digital games. That would be my first bit. And I would say that like conventional finance and then government related stuff, which is maybe most important, having the government assert to us various things with computational integrity. Sadly, I think that's going to be the last to come, even though it's most needed there. But okay, that's my answer.
Cool. Okay, so next one was actually my question.
Yeah.
Who from that early batch of students you mentioned, like that first batch when you guys just started working on it, have gone on to work on ZKPs? Oh, yeah.
Yeah. So, okay, obviously, I mean, the sort of ones most deeply invested are very famous. So formally, right, when we started this work, both Alessandro Chiesa and Madar Zvirza were students, right? And as was Ian Myers and Christina Garman, who weren't involved in our side of the team, but they're part of the Zero Cash paper. They're all of them now, they have pretty brilliant academic careers. There were the others that are sort of obvious candidates. So the very, very first batch, there were, so Arnab Bhattacharya is a faculty member. I can find the place, but he's doing theory. He's doing amazing theory these days, but he's not involved in ZKPs. That was the very first. I had 3 students who just did the summer project. None of them is involved in ZKPs these days, even though, I can tell you that they have an open invitation to sort of come and join StarCore. And each one of these students, these programmer students, when they were there, I always try to, have them stay and continue. Okay, so those were the very early ones. Then there were 2 other students, Arnon Yogev and Ohad Barta. They're sort of, moved on to other spaces. Even though Ohad Barta has now returned to Technion and is doing I think a master's with Yuval Ishai on ZKP, so he might return. Daniel Genkin is a faculty member in the US. I forgot the exact place. But that was the early. And then, of course, Michael Ryabtsev is my co-founder, chief architect. Ido Bentov is involved in many, many blockchain projects, Litecoin Foundation. He's in the Space Mesh and a whole bunch of other things. And another one is Shaul Kfir. He was not in the first batch. He's, I think, CTO of Digital Assets Holdings, which is a New York-based company that's using blockchain technology for traditional financial world.
Cool. Let's keep going. There's a bunch of more questions.
Okay, sorry. Okay.
All right. I'm going to close that one. Okay. Snarks and Starks are both incredible breakthroughs. What is the next improvement from a theoretical perspective that needs to be tackled? Example, proof size security. What about from an engineering perspective? For example, usability performance.
I would say, so okay, like proof size, first of all, for Snarks, there's not that, I mean, it's what we would often call epsilontics. Like, you're already at 200 bytes, like, it's not going to be less than 1 byte at 100. So I think for Snarks, proof size is not that interesting. I mean, one question that is not so much, I think, practically interesting, but sort of kind of cool is, can you get the best? This is a good question always to ask. Can you get the best of all worlds? Can you get the speed, scalability, transparency, post-quantum security, all the good things of a Stark with the proof size of a Graph 16 Snark? I think that's a very cool theoretical question. But I think that even if tomorrow you have the answer to that, and the answer is yes, here it is, it doesn't matter that much in terms of real world applications, because and I could go into that. Even though this is a question a lot of people are looking at, including myself, I don't think it's the the breakthrough. I do want to mention this. So there are huge breakthroughs happening all the time. In this huge branch of proof systems, we just had this amazing breakthrough occur. It has currently nothing to do with ZKPs or anything. It's this amazing result that the quantum version of multiple prover IP, which is basically the PCP model, the quantum version of that has a complexity class that is basically all of the computation that can be. This is an amazing breakthrough, and it's completely unexpected. It's causing a lot of waves. I urge everyone to read about it. There's a beautiful Quanta article. So that's the kind of breakthroughs that I applaud. It's really a spectacular result. You can search for MIP star, and just you'll get a whole bunch of. Curiously, it actually uses a bunch of results that we did in the PCP context.
Cool.
But then it does, it builds a whole new level of innovation on them. But it's good to know that some of the stuff that we did for those very different contexts are used there. So I would say the big breakthroughs are the unexpected stuff that we actually don't quite see. The reducing, making things more efficient, that's extremely important practically. But from a science theory point of view, it's less important. Yeah. Cool.
So should we keep going? Do you have time to go over a little?
Yeah.
Okay.
Look, I'm in quarantine. I can go nowhere.
All right. So just so everyone knows, on that ask a question on the lower bar, click on that, because then you can vote on these questions as well, so that you get kind of the next one you want to hear further up in the list. All right. So I'm just going to ask the next one. I think it's this one. Which feature of STARS do you see as being more relevant for business, zero knowledge or scalability?
Again, the one I see. Wait, the one I see.
Yeah, it moves around a little bit. But
okay. Now I see it. Which feature of STARS do you see as being more relevant for businesses, zero knowledge or scalability? So I would sequence them. I think that initially scalability is definitely the more important one, but I think that after that it's going to be scalability with privacy. Now, first of all, this is what we see when we try to interact with businesses. Partly, and this is also an explanation why StarCore for now is focusing mostly on scalability and not privacy. Part of the reason is that we have, pretty darn good alternative solutions for privacy, like, snarks and bulletproofs and, the whole bunch of other things that if you don't care about extreme scalability, about, larger and larger throughput and very efficient proofers, they are very good for use, and they are actually deployed. But still, I think that first we need scalability. Which is best delivered by these sort of symmetric STARKs, what we call, that are based only on symmetric crypto. But then you'll also want scalability with privacy.
Cool.
Oh, this one I like. Why were the papers rejected primarily? Oh man, I could speak about this for 5 hours. Why? Because the PC are a bunch of idiots. That's why. No, okay. PC means program committee. No, don't quote me on that.
You're only live.
I'm kidding. Look, anyone who has written any paper in the academic worlds can give you a whole lecture on why they were rejected and how it's always the program committee in the community that just doesn't understand the greatness. I don't think it matters that much. No, it's actually, it's funny, and at the time it was very frustrating to read this and say, oh man, can't they see this, blah, blah, blah. But it's part of the process, no? I mean, look, if something is unexpected, or if, you take something that is in one context, like let's say the PCP theorem, and you try to import it to this other universe and world of, let's say, real world cryptography that doesn't really do that stuff or understand it. So now both worlds are unhappy. We're all, myself included, we're sort of conservative and like the things that we know in the past. So when we see something that's really new, I mean, this is very true. Satoshi's paper would have been rejected from any conference in any journal in the world, flat out, right? No one would have accepted it. And you can name 50 different reasons why it would have been rejected. And it doesn't matter. It's still, probably one of the most amazing papers in computer science and beyond that in economics to have appeared. So.
All right. Which is the next one there? Ooh. So this doesn't update as quickly as the votes come in. I don't know if you see that. There's one with 6 votes.
I can toggle down, yeah.
Yeah. Oh, it jumped up.
Not for me, not yet. What do you see here now? What do you see as the strengths, weaknesses of low-degree text testing, proximity proof methods versus homomorphic encryption techniques? More tentatively, do both techniques have a long-term future, or one set of methods dominate? Okay, I'll answer the first question first. I think the low-degree testing proximity proofs will dominate. First of all, if most of the efficient homomorphic encryption stuff are based on some of them are based on things like number theoretic assumptions, or they require them, additively homomorphic encryption, so that whole thing falls down. There might be alternatives that are based on lattices, but they'll be less efficient. So just based on that, I think that long-term, they won't survive. They're also less efficient. In the midterm, I think we might, another analogy is what you see, let's say, in encryption. So yes, we do use number theoretic constructions, for instance, in SSL handshakes, but we use them for the minimal amount of time that we can, and to agree on a key, and then we move to this more efficient form. So I think that in the long term, even if quantum computers and attacks aren't there, and I do believe that we will find attacks in some of these constructions, you would still want to minimize your use of them to the particular things they're good at. The weakness of low degree testing with respect to the other methods, I know of one weakness, which is that the proofs that you get are larger by roughly 2 orders of magnitude from the fastest, the shortest snarks, and 1 order from some other constructions. But that's the only disadvantage I'm aware of. Everything else are advantages. They have greater speed, fewer assumptions. They're more agile in terms of the kind of constraint systems you can write with them, and so on and so forth. So, great question.
Where are we now? Shall we do this one? The one at the top now?
Today, is there an efficiency for the PCP tough knot? Right?
Mm-hmm.
So this is an amazing question, and it's the one question I probably spent most of my career thinking about, like getting even better PCPs. If I had known a very good approach, I would have pursued it. I don't know. I'm not aware of ongoing promising work, but I'm sure that others are also thinking, and someday we'll have much better just plain old PCPs. But for now, there is a semi-efficient, the sort of the Ben-Sasson construction. You could make it work, and in certain settings, you would get something on which your computer won't be exhausted while it's proving. But it's just vastly less efficient than the what you can do with an interactive Oracle proof model in IOP. Is a pairing-based snark a PCP? Is it an IOP? Okay, so a PCP, a PCP is a very, the PCP model is a very clean but unrealistic model. It is a model in which you're given, the prover generates a very long proof to which the verifier has Oracle access to, okay? Now, a pairing-based snark is not a PCP formally. So the answer to the first question is no, it is not in this model. Is it an IOP? So the IOP model is one of the most general models there are. So the IOP model contains within it PCPs and IPs and so on and so forth. So it is a special case of an IOP, but an IOP allows you like much more strength than what you need in a snark. So the answer to the second question is formally yes, it is some form of IOP, But I wouldn't call it that because an IOP allows you a lot more strength, and sort of you don't need that when you're building a pairing-based snark.
Cool. I wanted to try something. I want to make this the bigger screen. I'm curious what happens for everybody. I guess it's just a bigger screen. All right, what's next? Here we go. We've moved from theory to practice. How has this move been? What are you personally working on at StarCore?
Okay, so these are great questions. For me, this move has been, and especially StarCore, is, I love academics, and I loved my work when I was a professor at Technion. Which I am no more these days. But like, I'm having the time of my life at StarCore. And this has many reasons. Like, you know, we have a great team, a lot of good old friends, a lot of good new friends, just a lot of fun. Now, what am I personally working on at StarCore? So a little bit of everything, I guess. So I have a list of science-related projects that keep getting postponed, and I feel really bad about that. And then I'm involved in a lot of the other stuff, you know, the strategy, some of the product discussions. By now, I think I can't really say that I'm deeply involved in low-level engineering or, you know, or in. I mean, as things grow bigger and bigger, there's only so much you could sort of actually do. I mean, part of it is actually they don't know to code, so you know.
Right. Next one. Regarding the PCP theorem, what do you mean? What do you mean with only 3 bits need to be read? Is that to get a soundness of 1/2? What would the amplitude to get arbitrarily high soundness?
Excellent question.
That's my attempt.
Not surprising. So formally what happens, that's a really great question. Formally what happens is that when you look at the PCP theorem and you care about deducing inapproximability results, which is the main thing the PCP theorem has been used in theory, not in practice. So you really care about 2 parameters. You want to minimize the number of queries, and you want to make the kind of query as simple as possible while minimizing at the same time the soundness error, okay? And what I meant was there's this stellar result, you know, one of the most famous about the PCP theorem. It's called Hastad's PCP. You can all look it up. It's, I think the title is Some Inapproximability Results by Johann Hastad. And there what he shows is that irrespective of the proof length, irrespective of the original witness length, you can transform it into a PCP so that with the price of 3 queries, and moreover, making the kind of query, you read these 3 bits, and what you do is compute their XOR, their exclusive OR. It's very important that you do that. Then every correct statement you can accept with probability 0.999%, 0.999. And your error probability is at most, 0.50001. And you can't do better than half. So this is nearly optimal. And then if you want to amplify it, so if you want to have your error probability smaller than 2 to the 120, you're going to need to read 360 bits. And actually, you can do a little bit better than that. There are other papers that show you can do slightly better than even reading 3 times the security parameter. Oh yeah, for sure. Would you care to comment on Ben-Sasson's law of the reasonable complexity for natural problems? Yeah. Well, okay. Yeah, this is something I researched very extensively and I have very strong opinions on. So I hope you, I hope I can hear the smirks going on. What I meant to say is that, I mean, the reason I tweeted it that day, there was actually one part of our construction that has a, an exponent of 13 in it. And my initial reaction, so it's in one of our papers, and my initial reaction to that thing was, look, there's no result ever that actually has an exponent of 13 in it, and that is the correct answer. So I thought I'd throw it out as a taunting tweet. But to this particular thing, the point counting on genus 3 hyperelliptic curves, I guess, but for the O log p to the 14 and the word algorithm, I don't understand anything about the rest. So I don't know what point counting means, genus 3 hyperelliptic curves. So I'm qualified, just as anyone else, to say, I would say there's room for improvement, right? That's what I would say.
You can skip over the one that's from me there because it was actually answered underneath it.
Okay.
There's 3 more. Do you want to just pick one?
Yeah, who are the authors of the Pinocchio? I can Google them up. But
it's answered underneath, actually.
Okay.
It's already there. That's why I just skipped that guy.
Okay. What have been the biggest challenges switching from a research role to an executive role? How did you try to solve these challenges? That's a great question. So luckily, as I said, I have all of these great friends and co-founders and so on. I mean, they're more qualified to answer this question. So some of them might say that till this day, I haven't completed the transition from a researcher to a responsible adult. I mean, I contest that statement, but I guess the biggest challenge, I remember very early on, like we just started the company and we sit at this meeting and our excellent VP of engineering, who's also a 30-year-old, we are friends back 30 years, Owen Katz, says, okay, let's have a 3-month program. And at the time, this was like, I was, there were very few people who understood what's going on, right? We have these engineers coming on. So people also look at me. And I remember coming back home and saying, this is amazing. There are people out there who can actually plan for 3 months into the future and think about what they're going to do in these various things. It was like complete revelation. So I would say that, to quote the Beatles, I get by with a little help from my friends. So anyone thinking about doing this thing, get some good friends who can help you along this transition.
That's good.
Okay. Starks for scaling often require batching of transactions, adding a non-custodial but centralized operator. How do you reconcile this with the decentralized goals of the blockchain? In the future, do you see all validators running Stark software to decentralize the batching? Amazing question. Okay, there are 2 answers to this, right? So let me restate it. I mean, this is the problem that I think Coda is actually trying to solve head on very soon. We're all watching in anticipation to see how they deal with it. Because let's restate the problem. You want a lot of people, let's say, just a lot of people to send their transactions, shielded or unshielded. And then you would like to have a prover somehow, batch and compress all of them to one thing, right? That's something that we're going to need. Now, this is a problem of coordination, right? You could do this in some round robin fashion. You could rely on a centralized service. Having a centralized service is not so bad, and I'll explain why. Because that centralized service cannot cheat. It could censor, so it's not ideal, but it's not as bad as a fully, right? There's a limit to what that centralized service could do. Now, there's this amazing research question that I have not invested any time in. I think it's highly interesting, but they don't know how to solve it, which is what is the right way to throw in game theoretic or economic incentives along with the correct sort of partitioning of labor in order to get a decentralized and efficient batching of a proof. I don't know. This is a great science question that I don't know to solve. I wonder if CODA might be a good team to ask because they're trying to solve it.
Do you want to do the one with 3 votes there?
Yeah. So what is the status of the Stark-friendly hash function work? Is there a leading candidate in your mind? That's a great question. So yes, there is a leading candidate that we are getting more and more comfortable with. That seems to be Rescue. We're not, completely sure about it. We're waiting for one very last piece of symmetric cryptanalytic work, we are making a lot of progress on writing the code. I hope that within 2 to 3 months it will be stable enough to do 2 things: send it to external auditors. And this is something we publicized a large number of times. We want to run a workshop for developers who want to start building on it. This is going to be open source code, high performance, C++ prover and verifier. We already committed to it running at a rate of at least 600, a proof of 600 hashes per second per core. So on a quad core, more than 2,400. We thought of doing this workshop in Israel, like with actual teams. Now this coronavirus thing is up in the air, but and that's another topic that we'd be very happy to speak about.
Cool. Right when you said that, Alan hurrayed in the chat when you said rescue. Anyway, so the last one, what is the current state of Skipper and how involved are you in this project?
So there's a website on which I think folks are updating from time to time research. I am not involved anymore in it. I believe that, so I think definitely Alessandro and his team are involved in it. And I don't know who else. I could look at the website again. But yeah, so my involvement right now with the Skipper project is 0. So I just want to say, I want to say this. I enjoyed it a lot. And as I said, I have nowhere to go. And I could say that, I really would like to give another talk on math or math intuition about, let's say, PCP, Fry, Deep Fry, and FFTs. And maybe also bring, some of my friends, researchers and collaborators, both from StarCore and outside, to sort of opine and explain this stuff. So
I think that sounds really good.
Yeah, and I don't know if you can. Okay, Anna, we'll discuss this later. Either we'll do it through your channel if we can sort of hijack all of it, or otherwise we'll find some other means. But yeah, and I want to thank everyone. I'm going to read now all the comments and see, because I couldn't read it while focusing on this thing. But
very cool. All right. So I think that wraps up the first crowdcast that we're doing the ZK Study Club as.
Yay.
Thank you so much for coming. This is super interesting. I think this link will still actually have this video on it. So we'll share this after and watch it.